There is a volcano on the eastern coast of Sicily that volcanology has never been able to fit into any of its standard categories. It is the largest active volcano in Europe. 1 million people live around it. Its eastern flank has been sliding into the sea for centuries. And in the last few weeks, 3 small signals appeared on it, all in the same observation window, all pointing toward the same part of the mountain. A new line of research says these signals are not noise. They are exactly what the framework predicts. Here is what is actually happening. Three things just happened on Mount Etna, on 3 different instruments, in the same observation window. None of them individually would be news. Together, they are the kind of pattern that Italy's National Institute of Geophysics and Volcanology, the agency that monitors this volcano out of its observatory in Catania, takes seriously. The first signal is a small cluster of earthquakes that appeared west of the volcano. The magnitudes are tiny, around magnitude 2. Nobody would have felt them. The depth is what matters. These earthquakes happened at approximately 28 kilometers below the surface. That is about 17 miles down. They are not in the shallow magmatic system that drives the routine fountains and ash plumes you have seen on the news. They are deep. They are in the part of the volcano's plumbing that, until recently, scientists could not really see inside of. The second signal is a faint thermal anomaly that just showed up inside the northeast crater. A recent Sentinel-2 infrared satellite image, the kind the European Space Agency's Copernicus program collects for monitoring active volcanoes from orbit, picked up heat in a crater that has been comparatively quiet for years. The southeast crater complex, on the other side of the summit, is where most of Etna's recent paroxysmal activity has been concentrated. The northeast crater has been the quieter neighbor, and now it is warming back up. The third signal is the location of the volcanic tremor. Volcanic tremor is a continuous low-frequency ground vibration that an active volcano produces as fluids move through its plumbing. The position of the tremor source, where the dominant energy is being generated, moves around the summit area as the system breathes. In the last few weeks, that tremor source has been drifting toward the northwest part of the summit, which is geometrically near the northeast crater that just started warming up. So you have 3 signals from 3 different instruments, all pointing toward the same part of the volcano. Something is happening on the northwest side of the summit. Something is happening at 28 kilometers depth on the western side of the volcano. And a research framework that has been building in the literature for the last several years says that this is exactly the kind of pattern Mount Etna should produce when it is doing the thing it is, apparently capable of reorganizing its plumbing from below. Before we get into why 3 small signals on a volcano this complicated actually mean something, you need to understand why they would normally not be a story at all. Mount Etna produces small earthquakes constantly. The summit craters fluctuate in thermal output on a near-continuous basis. The tremor source moves around the summit area routinely as the magmatic system breathes. Italy's National Institute of Geophysics and Volcanology logs hundreds of small events on this volcano in any given month. The vast majority of them resolve into nothing. Background noise on one of the most actively monitored volcanoes on the planet. What makes the current pattern different is the alignment. The 3 signals are not 3 random small events. They are 3 signals from 3 different instruments that all point to the same general part of the volcano, in the same observation window. While a research framework that explicitly predicts this kind of pattern is consolidating in the scientific literature. That alignment is the operationally meaningful piece. Each signal on its own would be routine. The combination is what shifts the situation from background to worth tracking. Here's what you need to understand about Mount Etna. For most of the last century, volcanology has sorted the world's volcanoes into 3 categories. Volcanoes that sit on places where the tectonic plates are pulling apart, like Iceland. Volcanoes that sit on top of hot spots, like Hawaii. And volcanoes that sit on subduction zones, where one plate is sliding underneath another, like most of the Pacific Ring of Fire. 3 boxes. 3 mechanisms. Almost every volcano on Earth fits cleanly into one of them. Mount Etna does not fit any of them. It has never fit any of them. The volcano sits on the eastern coast of Sicily, in a region where the African plate is grinding northward into Eurasia. There is subduction happening in the broader area, but the geometry is wrong. The volcano is not in the position the standard arc model would predict. The lava chemistry does not match what a normal subduction zone produces, and there is no confirmed mantle plume directly beneath it, so it is not a hot spot either. For decades, volcanologists have been trying to fit Etna into one of the three boxes, with various contortions of the standard models, and none of it has fully worked. A new line of research is now saying something different. It is saying that maybe Etna does not belong in any of the boxes because the boxes are incomplete. There may be a fourth category that nobody had drawn before, and Mount Etna may be the example of it. The framework is this. Beneath the eastern Mediterranean, at the top of the planet's upper mantle, there is a layer of rock that is partially molten. A few percent of the volume is liquid magma. The rest is still solid. Seismologists can image this layer because seismic waves slow down when they pass through partially molten rock. They call it a low-velocity zone. In most places on Earth, this kind of layer stays sealed in. The overlying crust is thick enough to keep it bottled up. The partial melt sits there, primed, for tens of millions of years, never reaching the surface. At Mount Etna, the seal is broken. The slab structure underneath Sicily, the descending piece of old oceanic crust that has been sinking into the mantle for tens of millions of years, is folded and deformed. There is published evidence that it may even be torn at its western edge, where Sicily sits. And that broken slab structure creates pathways, fracture networks, weaknesses, corridors that connect the deep, partially molten layer to the surface. Magma can use those pathways to escape, slowly, unevenly, through a system of conduits that themselves shift over time as the slab keeps deforming. That is the new picture. Mount Etna is not fed by a single magma chamber sitting at some specific depth. It is fed by a deep, partially molten layer that exists across a much wider region of the eastern Mediterranean upper mantle, leaking upward through whatever pathways the broken slab geometry currently allows. Volcanologists are calling it a leaking pipe model in informal language. The technical name will get sorted out in the journals. And here is the part that connects directly to the signals showing up right now. A volcano that is fed by a single magma chamber has a single, stable pathway. A volcano that is fed by a leaking pipe through a deforming slab has a network of pathways, and that network can reorganize over time. The chemistry of the lava can change. The location of eruptions can change. The active vent can shift from one crater to another. The deep earthquake clusters can appear in places that have been quiet, which is, point for point, what Mount Etna has been doing for as long as anyone has been keeping track. If you want evidence that Mount Etna's plumbing has been reorganizing for a long time, the easiest place to find it is in the lava itself. Because lava is, in the most direct sense, a piece of the volcano's engine that has come to the surface. You can pick it up, you can analyze it, and the chemistry tells you something about where it came from and how it got here. The Mount Etna geological record goes back about 500,000 years. The earliest Etna lavas, the ones from the deep past, were comparatively iron-rich and silica-heavy. The kind of basalt that most volcanoes produce when they are just doing the basic thing. Over time, gradually, with some back and forth, the chemistry shifted. The lavas became more alkaline. They picked up more potassium and more sodium. The current Mount Etna magma is what petrologists classify as a sodic trachybasalt, with elevated levels of those two elements compared to what a normal subduction zone volcano produces, and compared to what Etna itself was erupting hundreds of thousands of years ago. In a normal volcano, you do not expect this. A volcano being fed by a single stable magma source with a stable plumbing system should erupt similar lavas for most of its history. The chemistry should be roughly the same from one century to the next. Over 500,000 years, it might evolve a little. It should not drift from one fundamental basalt type to a different one. When that happens, it means either the source has changed, or the pathway has changed, or both. The leaking pipe model explains the chemistry drift cleanly. If Mount Etna is being fed by a broad, partially molten layer rather than a single chamber, and if the pathway through the broken slab is reorganizing over geological time, then the magma can start drawing from different parts of the source. The depth and percentage of melting can shift, and the route to the surface can change. All of that produces exactly the kind of compositional drift that Etna's lava record shows. The chemistry is the receipt. It documents that the engine has been reorganizing for as long as we have data, which brings the story back to the present. Because if the pathway has demonstrably reorganized in the past, then the question of whether it is reorganizing right now, whether the current signals are the early phase of another reorganization, is a question you have to take seriously. The signals are not random noise on a stable system. They are the kind of pattern a system that is known to reorganize would produce when it is in the middle of doing exactly that. There is a practical reason this framework matters, beyond the academic question of taxonomy. A volcano with a stable plumbing geometry is, for forecasting purposes, a tractable problem. You track the deformation. You track the seismicity. You look for magma moving through known conduits. The signs of an imminent eruption tend to follow recognizable patterns. A volcano whose pathway can reorganize is a fundamentally harder forecasting problem. The location of the next eruption depends on where the pathway is currently leading. Standard tools that assume a fixed plumbing geometry work less well when the geometry itself is in motion. What replaces those tools is closer monitoring, more sensitive instrumentation, and a willingness to track multiple parts of the system at the same time without committing prematurely to a single prediction, which is essentially what the Italian National Institute of Geophysics and Volcanology has been quietly building toward at Mount Etna for years. The unusually dense instrument network on this volcano is partly a consequence of the recognition that the standard tools alone are not enough here. The new framework is now putting a theoretical name on what the operational community already knew from practice. Etna requires more eyes, more instruments, more cross-checking, and more humility about what is going to happen next than a textbook volcano would. Mount Etna is not a remote volcano. The city of Catania, the second largest city in Sicily, sits at the southern foot of the mountain. The metropolitan area is approximately 1 million people. There are dozens of towns scattered across the volcano's flanks at various elevations. Zafferana Etnea, Nicolosi, Lingua Glossa, Bronte, Randazzo, Adrano. Some of these towns have been there for centuries, rebuilt after past eruptions, sometimes more than once. The agricultural land on Etna's slopes is some of the most productive in Sicily, because volcanic soils are extraordinarily fertile. Etna's wine industry is internationally recognized. Etna's pistachios, grown on the western flank, sell at premium prices in global markets. This is also a working tourist destination. The summit area is accessible by cable car and by guided trail. Hikers go up there in summer. Skiers go up there in winter, sometimes within view of incandescent lava at the active craters. The Etna Park visitor infrastructure operates year-round. On any given day, depending on the season, there are anywhere from a few hundred to several thousand people physically on the volcano. And Catania Fontanarossa Airport, one of the busiest airports in southern Italy, sits at the southern foot of the volcano. Etna ash closes this airport regularly, sometimes for hours, sometimes for days. The Toulouse Volcanic Ash Advisory Center issues advisories for Etna ash on a recurring basis throughout the year. Aviation routes through the central Mediterranean are adjusted accordingly. This is a normal part of operating in this region. The reason all of that matters is that any change in the volcano's behavior, any reorganization of the plumbing system that shifts where the next eruption will open, or how big it will be, or how much ash it will produce, has direct economic and human consequences. Italy's National Institute of Geophysics and Volcanology runs one of the most comprehensive monitoring programs of any active volcano on Earth here. They have a permanent seismic network of roughly 35 to 45 stations on and around the mountain, continuous GPS, tilt meters, gas spectrometers, satellite thermal imagery, seafloor instruments on the offshore part of the flank, which we will get to in a minute. The investment is justified by the exposure. Etna is the kind of volcano where the cost of being surprised would be very high, so the country pays the cost of paying attention. There is one more part of the story you need to understand, and it does not depend on any new research, because it has been known for decades. The eastern and southeastern flank of Mount Etna is moving, not metaphorically, measurably. The entire flank is sliding eastward toward the Ionian Sea at rates of several centimeters per year. The way this gets measured is with a satellite radar technique called interferometric synthetic aperture radar, or INSAR. A radar satellite passes over the same patch of ground on repeated orbits. Bouncing radar pulses off the surface and recording the precise phase of the returning signal each time. If the ground moves between two passes, that motion shows up in the phase data with millimeter precision. Combine that with ground-based GPS stations installed across the volcano, and you get a high-resolution picture of how the flank is deforming. What that picture shows is that the eastern flank is one large mass of rock and volcanic material moving consistently toward the sea. The motion is slow in any given month, a few centimeters per year, which nobody would notice walking around on it. But the volume that is moving is enormous. The sliding sector covers a large fraction of the volcano's eastern flank, villages on it, agricultural land, roads. And the part of the sector that goes underwater, which is where this gets unsettling, continues offshore. The eastern flank does not end at the coastline. The volcano is built on a basement that slopes eastward, and the sliding sector tracks the basement. When you cross the shoreline, you are not crossing the edge of the flank. You are crossing the edge of the visible flank. The underwater extension keeps going. It goes down to approximately 1,500 meters below sea level. That is almost 5,000 feet below the waterline. And it is still part of the same sliding sector you can stand on in the villages above. The Italian National Institute of Oceanography and Applied Geophysics has mapped the offshore part with side-scan sonar and multi-beam bathymetry. They have identified the geometry, the headwall scarps, the transverse faults, the lobate scarps on the seafloor that are the underwater signature of the same kind of deformation happening above. They have installed seafloor monitoring instruments on the underwater part of the flank, so the geodetic measurements continue down there in real time. This is not a routine investment. Most volcanoes in the world do not have seafloor geodesy on their submarine flanks. Mount Etna does, because the hazard is recognized as real enough to justify the cost. The hazard is not the slow slide itself. The slide has been happening for centuries. The hazard scenario is sudden failure of a portion of the sliding sector, a flank collapse that would displace a large volume of water and generate a tsunami in the Ionian Sea. We know what that kind of event can do because it has happened elsewhere. Stromboli, north of Sicily, had a flank collapse during an eruption on December 30th, 2002. The resulting tsunami damaged the coast of Stromboli itself and reached Sicily and Calabria. Anak Krakatau in Indonesia had a flank collapse during an eruption on December 22nd, 2018. The tsunami that followed killed more than 400 people in Java and Sumatra with no earthquake warning, because the trigger was a flank collapse rather than a quake. Ritter Island, off Papua New Guinea, lost its western flank in 1888 in a single massive collapse. The tsunami produced 15 to 50 meter run-ups on adjacent islands and propagated damaging waves out to about 600 kilometers. None of those volcanoes is Mount Etna. The scenarios are not identical. The probability of a catastrophic Etna flank collapse on any given day is low, but it is not zero. And the reason Italian agencies invest in continuous seafloor monitoring of the underwater portion of the flank is precisely so that if the slow grinding motion ever shifts toward a faster motion, the warning comes early enough to do something with it. The connection back to the central story is direct. A volcano whose deep plumbing can reorganize is a volcano whose surface stress field is not constant. Changes in the deep pathway can shift the load on the flank above. The flank slide and the current small signals are not separate problems. They are two faces of the same mobile volcano. And what is happening deep below the western side of the summit right now is, in principle, capable of affecting what is happening on the eastern flank that is already in motion. Let me be clear about where the operational situation actually sits. Italy's National Institute of Geophysics and Volcanology has not raised the alert level at Mount Etna. They have not issued any warning of imminent activity. There is no evacuation order, no flight diversion, no closure of public infrastructure. The current monitoring posture is at the level of paying close attention, not at the level of acting on the alert. What they will be watching for over the coming weeks is whether the three signals develop further. Whether the deep western earthquake cluster grows in number, in magnitude, or in spatial extent. Whether the northeast crater thermal signature strengthens or fades. Whether the tremor source continues drifting toward the northwest summit area or migrates back to its previous configuration. They will also be watching the gas chemistry, because the chemistry of gases coming out of the summit fumaroles is one of the most sensitive indicators of changes in the deep magmatic system, often showing reorganization before any of the other instruments do. If the signals continue to develop, the next operationally meaningful question is where on the volcano the system might be heading. A summit paroxysm, a routine fountain eruption from one of the active craters, is the most common kind of response, and one that would not be unusual for Mount Etna and Enims to the craters. A flank fissure opening on one of the slopes is the higher impact scenario, particularly if the fissure opens low enough on the volcano to threaten populated areas. A significant change in the eastern flank slide rate would be the longest-term concern. If the signals fade, on the other hand, the most likely outcome is that the system was doing what the new research framework predicts is its normal behavior, reorganizing slightly, then settling into a new configuration, with no surface change visible during this particular round of motion. What you should actually do with all of this is the same thing you would do with any developing geological story. Pay attention to the bulletins that the Italian National Institute of Geophysics and Volcanology publishes on its website. The information is public. The updates are continuous. If the situation changes meaningfully, that change will be announced, and it will be announced before any reasonable source on social media has it. The experts on this volcano are in Catania, working with the data in real time. Their bulletins are the ground truth. Anything you read or watch about Mount Etna, including this video, is downstream of what they are saying. Mount Etna is one of the most studied volcanoes in the world, on a coastline where 1 million people live, with a behavior pattern that has been resisting easy classification for as long as anyone has been keeping records. A new research framework just argued that the reason it is hard to classify is that it does not match any of the standard categories. 3 small signals just appeared on the volcano that fit that framework. The eastern flank is still moving. The monitoring is good. The data will keep coming in, and we will be tracking this as it develops.